All right, guys, we're gonna get started here today. First thing, I hope you guys had a great weekend. And that you had, again, I hope you had an opportunity to relax a little bit, and that it wasn't spent all working or doing homework or things for school. But if it was, I'm sorry. So today the goal is we're gonna go over the last little chunk of section 9.3. Then we'll begin section 10.1. My plan for this week is that today and tomorrow we'll get through the lesson, like lecture parts of section 10.1 and 10.2, because it's essentially just building off of what we've done in the previous few chapters. Next week we'll do practice problems like within Desmos or Pear Deck, or problems that I have. You know, I'm a math teacher, I got problems. We'll do practice problems for section 10.1 and 10.2. So that we get to do that. Then the last week of April, I want to use that week to go through the AP digital testing environment, and hopefully be able to have you guys do like a practice test on one of the 2 days that we meet. So that's kind of the idea for April. We'll get through all of chapter 10. We'll do some AP prep stuff. And then starting May, we'll get through the last few chapters. You know, hopefully it's all well and good. Okay. So to get through the last chunk.
You doubled up here, Mr. Mosley.
To get through the last chunk of section 9.3, that is in Desmos. So I'm going to drop that link to the Desmos activity into the chat again. And that is just, honestly, if you want to follow along with that, that's fine. There's nothing for you guys to do in the activity. Actually, then that doesn't make sense. We're not going to drop the link. I'm just going to share my screen and show you guys the stuff. We'll get through the end of section 9.3. So if you're taking notes, please, this is an opportunity to take a few other things into your notes for chapter 9 that we need to be aware of. And then we'll move on to chapter 10. All right, so let's do my silliness here. We'll start there. We'll go to share my screen. Here we go. That's what I want. Leave that, and we're good here, and we're excellent. All right, excellent. All right, as usual, if you have any questions, please let me know. Raise your hand, shout out, something. If you need clarification, again, ask. All right, so here we go. This is the last chunk of section 9.3. This kind of picks up where we left off for this slide here. Two-sided tests and confidence intervals. The connection between two-sided tests and confidence intervals is even stronger for means than it was for proportions. And that's because both inference methods for means use the standard error of the sample mean in the calculations. Right, and the standard error is this part in the denominator for the test statistic, the sample standard deviation divided by the square root of the sample size, right, which exists in both formulas. We didn't see that same correlation between proportions, between tests and confidence intervals with proportions, but with means, it's a little bit stronger. All right, a two-sided test at significance level alpha, say alpha equals 0.05, and a 100 times 1 minus alpha percent confidence interval, 95% confidence interval if alpha equals 0.05, gives similar information about the population parameter. When the two-sided significance test at level alpha rejects the null hypothesis, the 100 times 1 minus alpha percent confidence interval for mu will not contain the hypothesized value for mu. All right, so what that means is that, say we have a alpha of 0.05, that means we have a 95% confidence interval. If we reject the null hypothesis, that means our confidence interval does not contain the null hypothesis. All right, so we can, and that's only with a two-sided test. But that means that it gives us a lot more information. If we reject the null hypothesis, we have an idea of what's plausible by finding obviously the confidence interval. But we know that that value is outside the confidence interval. So So it gives us a little more information about what the answer could be, what the plausible values are. When the two-sided significance test at levels alpha fails to reject the null hypothesis, the confidence interval for mu will contain mu naught. Right. So again, if we fail to reject, that means the null hypothesis exists within our confidence interval, so it is a plausible value. So we have that connection that exists within two-sided tests and confidence intervals that doesn't exist the same way with two-sided tests and confidence intervals for proportions. This only kind of really applies for means, right? See, we need a moment to write anything down from this screen. All right. We shall pause. So then the other thing we can kind of do with our significance test for means is use paired data. Right? This is having to do with comparing things. Comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals result in paired data. It's almost like if we go reach way back to things that we've seen in the past, like a matched pair block, right? We were doing blocking for our study. When paired data result from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the differences in each pair. If the conditions for inference are met, we can use one sample t procedures to perform inference about the mean difference. And we use mu with the subscript d for difference. These methods are sometimes called paired t procedures, but we're still using the same inference method. We're using the one sample t procedure. Right. And we're going to watch an example about this that shows how to do a paired data one sample t procedure. It takes about 4 minutes, so that's not too bad. And I should have this set up to where volume comes through, so let me know if you can't hear it.
Hi, this is Jason Molesky. Let's take a look at paired data and one sample t procedures. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. Now, during one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo was randomized, and at the end of each 2-day period, a test for depression was given to all 11 subjects. Now, researchers wanted to know if being deprived of caffeine would lead to an increase in depression. Now, this table contains data on the subject scores on a depression test. Higher scores show more symptoms of depression. So we have our 11 subjects here and their depression scores on the first test. We also have our 11 subjects and their depression scores on the placebo test. And then we also have the difference between those scores. And we went placebo minus caffeine because for the most part, the placebo scores are greater than the caffeine scores, and that resulted in positive values for the most part in the difference column. Now, why did researchers randomly assign the order in which subjects received the placebo and caffeine? Well, researchers want to be able to conclude that any statistically significant change in depression score is due to the treatments themselves and not to some other variable. One obvious concern is the order of the treatments. Let's suppose caffeine were given to all the subjects during the first 2-day period. What if the weather were nicer on these 2 days than during the second 2-day period? Well, the researchers wouldn't be able to tell if a large increase in the mean depression score is due to the difference in weather or due to the treatments. Random assignment of the caffeine and placebo to the 2 time periods in the experiment should help ensure that no other variable is systematically affecting the subject's responses. Now let's carry out a test to investigate the question. If caffeine deprivation has no effect on depression, then we'd expect the actual mean difference in depression scores to be 0. That is, the scores when the subjects were on caffeine would be pretty much the same as the scores as when they were on the placebo, so therefore the difference would be 0. So our null hypothesis is that the mean of the differences is 0, while the alternative hypothesis is that the mean of the differences is greater than 0, where the true mean difference is defined by mu sub d, and we did note that that was placebo minus caffeine. Now, because no significance level is given, let's use alpha equals 0.05. Well, to use a paired t-test, let's first check our conditions. We note that the researchers randomly assigned the treatments placebo, then caffeine, caffeine, then placebo to the subject, so that condition is met. Since we aren't sampling, it's not necessary to check the 10% condition. And when it comes to the normal large sample condition, we don't know whether the actual distribution of difference in depression scores is normal, so we're going to have to do a little extra work here. With such a small sample size, we need to examine the data to see if it's safe to use T procedures. Well, here's a histogram, a box plot, and a normal probability plot of these 11 differences. The histogram itself does have an irregular shape with so few values. The box plot shows a little bit of right skewness, but no outliers here, and the normal probability plot is slightly curved, indicating there is some slight skewness. However, with no outliers and no strong skewness, the T procedure should be pretty accurate. Now we entered the differences in list 1 and then used the calculator's t-test with the draw command to perform this test. We see our statistic here is 3.53, and we get a p-value of 0.0027. That's the area to the right of t equals 3.53 on the t distribution curve with 10 degrees of freedom. Now, because the p-value is 0.0027, and that's significantly less than 0.05, we reject our null hypothesis. We have convincing evidence that the true mean difference, placebo minus caffeine, in depression score is positive for subjects like these. Now, for some additional practice with paired data and one sample T procedures, try exercise 85.
All right. Are there any questions on this example? Anything you'd like me to explain or refer to or give further detail on? So lastly, we need to use our tests wisely. Right? Carrying out a significance test is often quite simple, especially if you use a calculator or computer. Using tests wisely is not so simple. Here are some points to keep in mind when using or interpreting significance tests. How large a sample do I need? Smaller significance level requires stronger evidence to reject the null hypothesis. Higher power gives a better chance of detecting difference when it really exists. At any significance level and desired power, detecting a small difference between the null and alternative parameter values requires a larger sample than detecting a large difference. Okay. So if the differences are much smaller and we want to know whether or not it's significant, we need a larger sample. Statistical significance and practical importance. When a null hypothesis, no effect or no difference, can be rejected at the usual levels, alpha equaling 0.05 or alpha equaling 0.01, there is good evidence of a difference. But that difference may be very small. When large samples are available, even tiny deviations from the null hypothesis will be significant. Right. Beware of multiple analyses. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide that what difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. Okay. So it's kind of saying like the context of this thing matters. Sometimes finding significance isn't really that important based on the study that you're doing, but that again depends largely on the context. Does anyone need a moment to write anything down from this screen or the last screen, because I went a little fast past the last screen? All right. So that is the end of chapter 9 altogether. Those are the last couple things we need to go over. All right. And that leads us to getting into chapter 10. Before we jump into chapter 10, is there any questions or anything you'd like clarification on having to do with chapter 9? Or significance tests for population proportions and means? Okie dokie. Then we'll jump right into chapter 10. Which will go here. Alrighty. So chapter 10 is comparing two populations or groups. All right, now this is different than the paired data that we just saw. That is having to do with kind of like dealing with the same population. This is now getting into comparing different populations or groups, right, which uses a slightly different procedure. We're going to start with comparing two proportions. Right. The goals of this section are going to be able to describe the shape, center, and spread of the sampling distribution of the difference of two sample proportions, determine whether the conditions are met for doing inference about proportion 1 minus proportion 2, construct and interpret a confidence interval to compare two proportions, and perform a significance test to compare two proportions. All right. These 4 things are things that we've done kind of one chapter at a time, and now we're kind of bringing them all together into a single space. So first, suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. Let's call these parameters of interest P1 and P2. The ideal strategy is to take a separate random sample from each population to compare the sample proportions with that characteristic. What if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of successes in the 2 treatment groups to make the comparison. All right, so this is giving us 2 scenarios where we would use the difference between populations, right? And we have population proportions P1 and P2 for our characteristic and also for treatments. So we need a moment to write anything down. And here's the notation that we can use here. So we have population or treatment 1. The parameter is P1. The statistic is P hat sub 1. Sample size for population 1 is N1. Similarly, for population or treatment 2, we have parameter P2, statistic P hat 2, sample size N2. Right. We use the subscripts 1 and 2 in this case to differentiate between the 2 different proportions and the notation going along with each one. So those subscripts become very important. Excuse me. So we need a moment to write any of that down. So to explore the sampling distribution of the difference between two proportions, let's start with two populations having a known proportion of success. At school 1, 70% of students did their homework last night, and at school 2, 50% of students did their homework last night. Suppose the counselor at school 1 takes an SRS of 100 students and records the sample proportion that did their homework. School 2's counselor takes an SRS of 200 students and records the sample proportion that did their homework. Notice that our sample sizes in each case is not the same. Right, so it doesn't necessarily need to be the same sample size here. What can we say about the difference p hat 1 minus p hat 2 in the sample proportions? Right, and using Fathom software, which is a software that does statistical modeling, which we don't have access to because it costs money. We generated an SRS, but the textbook people do, of 100 students from school 1 and a separate SRS of 200 students from school 2. The difference in sample proportions was then calculated and plotted. We repeated this process 1,000 times, right? So we get the sampling distribution for p hat 1, sampling distribution for p hat 2, and the sampling distribution for p hat 1 minus p hat 2. All right, so this is drawing back to what we've seen in chapter 7 with our sampling distributions. The sampling distribution, right, is when we repeat the same sampling process over and over again, and we create a distribution showing essentially what the expected outcome would be if we did this thing over and over and over again. All right, each of these is approximately normal. Right, the mean for p hat 1 is equal to p1, which is 0.7, which is what we see here on the graph. Right, and so that, remember back in chapter 7, we know the population proportion. In this case, it's 0.7. And if we have a good, what's the right word, estimator, right, which in this case is p hat 1, it should be the mean of that estimator is the same as the population proportion. Right, we also can then get the standard deviation for p hat 1, which is p1 times 1 minus p1 divided by n1, take the square root of that whole thing, we get 0.0458. Right, we do the same procedures for the rest of these. Right, we have a center of 0.5 for school 2, spread of 0.0354, and then the difference, the mean is 0.2. And again, the mean is simply the mean of P1 minus the mean of P2. Right, 0.7 minus 0.5, 0.2. Right, the standard deviation is the square root of the variance of P1 plus the variance of P2. And that again is something, we're using the rules that we have from chapter 6 on random variables at that point, which we're going to do some review on this, but not today. Any questions about where all these things came from? So what do you notice about the shape, center, and spread of the sampling distribution of P1 minus P2? They're all normal. That's kind of nice. We're gonna move on. So both p hat 1 and p hat 2 are random variables. The statistic p hat 1 minus p hat 2 is the difference of these two random variables. In chapter 6, we learned that for any two independent random variables, x and y, the mean of x minus y equals the mean of x minus the mean of y, and the variance, notice this is variance, of x minus y is equal to the variance of x plus the variance of y. Sampling distribution of the difference between sample proportions, all right? So we're going to choose an SRS of size N1 for population 1 with proportion of success P1. My light went out. Come on, lights. There we go. And independent SRS of size N2 from population 2 with proportion of success P2. We will have a shape when N1 P1, N1 times 1 minus P1, N2 P2, and N2 1 minus P2 are all at least 10. This is our large counts condition. The sampling distribution of P hat 1 minus P hat 2 is approximately normal. Enter. The mean of the sampling distribution is proportion 1 minus proportion 2. The spread, the standard deviation of the sampling distribution of P hat 1 minus P hat 2 is the square root of P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. Right? This is the variance of P1 plus the variance of P2. As long as each sample is no more than 10% of its population, that's our 10% condition. So again, when we're doing the sampling distribution, we are still using the large counts condition and the 10% condition in order to get these values. We have to check these conditions. Same as we had to do in chapter 7. Does anyone need a moment to write anything down? Please raise your hand. And again, here's a visual. We have our sampling distribution of P hat 1 minus P hat 2. We get a normal distribution. This is all the plausible values for P1 hat minus P2, or all the values we got from our sampling. Standard deviation, and our mean is the center. So we have that same context that we saw previously, right? School 1, 70% of students did their homework. School 2, 50% of students did their homework. We have an SRS of 100 from school 1, SRS of 200 from school 2. We need to describe the shape, center, and spread of the sampling distribution of P hat 1 minus P hat 2. All right, because N1 P1 equals 70, and N1 times 1 minus P1 equals 30, N2 P2 is 100, and N2 times 1 minus P2 is 100, are all at least 10. The sampling distribution of P hat 1 minus P hat 2 is approximately normal. Right, that's what our large counts condition tells us. When that is met, the distribution should be approximately normal. Its mean will be P1 minus P2, which is 0.7 minus 0.5 is 0.2. And the standard deviation is the square root of 0.7 times 0.3 divided by 100 plus 0.5 times 0.5 divided by 200 is 0.058. These three parts obviously describe shape, center, and spread. This is all we need. Is there anything I can clarify on this so far? Because this right here is essentially chapter 7. Right, this is applying the things that we saw in chapter 7 to difference between two proportions, in which case we're combining random variables using the ideas we found in chapter 7. All right, next we're going to move to chapter 8 with this idea and do confidence intervals. Right. So when data come from two random samples or two groups in a randomized experiment, the statistic P hat 1 minus P hat 2 is our best guess for the value of P1 minus P2. We can use our familiar formula to calculate a confidence interval for P1 minus P2. Again, statistic plus or minus critical value times the standard deviation of a statistic. So when the 10% condition is met, the standard deviation of the statistic is p hat 1 minus p hat 2 is the same thing that we just saw on the previous example, right? Square root of p1, well, it's a minor change because now we use our, sorry, never mind, no difference. P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2, that is our standard deviation. If the normal condition is met, we find the critical value Z star for the given confidence level from the standard normal curve. And again, we have the same three conditions that we need to check before constructing a confidence interval about a difference in proportions. We need to have the random, 10% and large counts conditions. The only difference now is that we have to check for both populations. So we have to check the 10% condition twice for population 1 and population 2. And we check the large counts condition for population 1 and population 2. So there's just an extra step on those. Because we don't know the values of the parameters P1 and P2, we replace them in the standard deviation formula with the sample proportions, and the result is the standard error of the statistic P hat 1 minus P hat 2, which is the square root of P hat 1 times 1 minus P hat 1 divided by N1 plus P hat 2 times 1 minus P hat 2 divided by N2. Right, so we're replacing the parameter P1 with the statistic P hat 1, and the same for P2. Can you raise your hand if you need a moment to write any of this down? So we then use the inference method, the 2 sample Z interval for a difference between two proportions when the conditions are met. An approximate C% confidence interval for P hat 1 minus P hat 2 is P hat 1 minus P hat 2 plus or minus Z star times the square root of all this fun stuff, right? Our standard error here, square root of where Z star is the critical value for the standard normal curve with C% of its area between negative Z star and Z star. Right, so again, we would be using table A in this case, right, depending on our confidence percentage. Is there any questions? Anything I can clarify here? Does anyone need a moment to write any of this down? So that leads us to then Chapter 9, significance tests for P1 minus P2. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form H naught such that P1 minus P2 equals hypothesized value. We'll restrict ourselves to situations in which the hypothesized difference is 0. Then the null hypothesis says that there is no difference between the two parameters. All right, so H naught such that P1 minus P2 equals 0, or alternatively, H naught such that P1 equals P2. All right, so we can list the null hypothesis in either of these ways. The alternative hypothesis says what kind of difference we expect. Right, we can have the alternative being that the difference is greater than 0, the difference is less than 0, or that it's just not 0, meaning we have a two-sided significance test. Okay, so we have essentially all the same things that we just worked with in chapter 9, except now we're dealing with differences in proportions. And the cases that we're going to be looking at, we're assuming a difference, or our null hypothesis will have a difference of 0, meaning no difference. So, would anyone like a moment to write any of this down? All right, so again, same 3 conditions for performing a significance test about the difference in proportions. Random 10% in large counts, and just like when constructing a confidence interval, we have to check these conditions for each population. All right, do not forget to check it for both populations. There's a little bit extra to check. Right, to do a test, standardize p hat 1 minus p hat 2 to get a z statistic. Right, our test statistic is statistic minus parameter divided by standard deviation of statistic. In this case, it'll be z equals p hat 1 minus p hat 2, whatever that difference is, minus 0. So p hat 1 minus p hat 2. And divided by the standard deviation of the statistic. And again, our standard deviation should still be that square root of, p hat 1 times 1 minus p, blah, 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 blah. Lots of different p's. All right, if the null hypothesis is true, the 2 parameters are the same. We call their common value p. We need a way to estimate p, so it makes sense to combine the data from the 2 samples. The pooled or combined sample proportion is count of successes in both samples combined divided by count of individuals in both samples combined. All right, so we have p hat c equals x1 plus x2 divided by n1 plus n2. This is in the case that the null hypothesis is true. Right. So you need a moment to write anything down. And we have our inference method here, the 2 sample z test for the difference between 2 proportions. Suppose the conditions are met. To test the hypothesis H not such that P1 minus P2 equals 0, first find the pooled proportion P hat C of successes in both samples combined, and then compute the z statistic. Right. Z equals p hat 1 minus p hat 2 minus 0 divided by the square root of p hat c times 1 minus p hat c divided by n1 plus p hat c times 1 minus p hat c divided by n2. So the numerator in both of these is the same. The only difference is the sample size here. Find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis H sub A. This part is the same as what we did previously once we have that z statistic. Right. We'll get a p-value. So we need a moment to write anything down from this screen. So we have inference for experiments. Many important statistical results come from randomized comparative experiments. Defining the parameters in experimental settings is more challenging. Most experiments on people use recruited volunteers as subjects. When subjects are not randomly selected, researchers cannot generalize the results of an experiment to some larger populations of interest. Researchers can draw cause and effect conclusions that apply to people like those who took part in the experiment. Unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. Okay, so this is providing us a scenario in which case we don't check the 10% condition. And that is when the subjects in an experiment are not randomly selected. Okay. And that actually brings us to the end of this presentation. Right, I know that that was a lot and it came real fast. Is there anything you'd like me to go back to? Or any questions that you have? Anything you'd like clarification on so far? Okay. So again, I know that was a lot. So we're gonna let that kind of marinate there. Tomorrow we'll look at basically a lot of similar ideas dealing with means, the differences in means comparing to population means. And hopefully tomorrow I'll actually be able to do some examples for you guys so you can kind of see how these things play out and how they work in an actual example. And again, like I said, next week we'll do practice with proportions and means and differences and all these fun things. All right. Does anyone have any other questions, comments, concerns, anything at all? All right, well then that brings us to the end of the class today. I hope that it wasn't too overwhelming. Again, we will go over this again. If you do have any other questions, comments, or concerns, please make sure to let me know. Otherwise, have a great rest of your day and I will see you tomorrow.